thanks everybody for joining us here today. It's good to be back in the new year and as things get back in full swing. We decided coming off of PHN in Denver and the panel that we put together around fire resilient design, that it might be a good idea to try and connect the principles of Passive House with fire resilient design, because there's not really a component there that does that. I will start off by talking a little bit about our material. If you're not familiar, I think probably most of you are, but I'll give you the quick and dirty. We are 60% basalt rock, one of the most prevalent mineral resources on the planet, 40% steel slag, so recycled material from post-industrial content, right? So from the manufacturing of steel, melted at quite a high temp, spun into fibers. Those fibers are collected and treated with a binder, which lends the material not only density, so we have materials that go all the way from very light density that we would use for acoustic and fire mitigation in interior wall sections, all the way to quite dense material that would go in roofing and or behind EFIS applications. But it also makes that material quite hydrophobic, which makes it pretty ideal for rain screen applications or anything on the exterior and the roof. So we thought that with Passive House becoming more and more prevalent in codes and in stretch codes, I sit in Massachusetts, where Passive House has become pretty ingrained in our code, especially for multifamily residential. We see increased incentives for building passive, especially in the wake of events like the Marshall Fire. There are more designers are generally becoming more aware of the benefits of passive design. So while those 5 principles that we use in Passive House that make us a more energy efficient, comfortable, and resilient design in the face of climate change, we're seeing increasingly severe climate events, and those, of course, come with wildfire. As I mentioned before, local codes are also driving changing our design around fire resilient design in urban areas, in suburban areas, and even in rural areas. And so, we need to look very carefully at that need for a more resilient and efficient thermal barrier, along with the fire consideration. Sorry, a small pause here. So whether we're talking about Type 5 construction or typical commercial construction, newer concepts, CLT is becoming quite prevalent. Those approaches are generally looking at a perfect wall. Hey, Antoine, can you, there we go. Or whether we're talking about more traditional Passive House designs, interior insulation strategies, especially when as it applies to retrofit construction, or whether, what we're mostly seeing, right, that split insulation scenario. All of these are requiring more and more insulation, and that makes things a little bit more complex, not only from a fire perspective, but also as we're mostly adding insulation to the outside of the building, where, of course, it's most effective. So as we look at fire safety and we're adding more and more insulation to our builds, depending on how we use that insulation, where we use that insulation, we have a pretty significant impact on what's happening with fire. We want to make sure that we're building for the long haul, right? That we're using products that don't deteriorate over time when it comes to their efficacy, both in the from the thermal standpoint, but also from a fire standpoint. And then, of course, we want to make sure that we're using materials that don't contribute to fire, to making it tougher when it comes to fire resistance. And perhaps most importantly, allowing extra time for when a fire event does occur, both for occupants to be able to get out of the building, but also for first responders to do their job. So Antoine's going to take it away from here, and he will talk first about non-combustibility and surface burning characteristics of different materials. We'll look at building assembly fire resistance ratings and balancing fire performance along with energy efficiency. And to quote Zach, things will get nerdy here. So I'm going to let Antoine take it away.
Thank you, Rob. Good morning, everyone, or good afternoon for maybe some of us who are on the East Coast. Yes, things may get a little nerdy, so I think it's okay to take some of the questions throughout if it's directly applicable to the slide. Otherwise, obviously, we'll be there after the presentation to try to answer as many questions as possible. So the first thing I would like to do is talk about the performance of product itself, and then move to the assembly and finish with the facade. So the first stop is non-combustibility and surface burning characteristics. Before doing this, I would like to come back to the very, very basics of what does it mean for a product to be combustible or non-combustible. So these are actual definitions. They're not from the codes. They are not necessarily intended to be technical definition. They are, typical definition. I think I got them from Merriam-Webster, if I recall. But they're very the regular everyday definition. So combustible is an adjective that defines a material that would be capable of undergoing combustion. A non-combustible material, on the other hand, is a material which, in the form in which it is used and under the condition anticipated, will not ignite, burn, support combustion, or release flammable vapors when subjected to fire or heat. So obviously, talking about non-combustible materials means a lot of things, very, very specific and extremely technical. And, in the case of ROCKWOOL insulation, for instance, it's not as simple as just saying it's made of stone, it doesn't burn. There is a lot of things behind having a product that is non-combustible. Non-combustibility is pretty much everywhere in the code. Whether you're looking at the International Building Code, the International Residential Code, the National Building Code of Canada, the Ontario Building Codes, pretty much any codes you can think of in North America, you will see reference to non-combustible written in one word or two words, depend on the country and the states and provinces. But basically, they are characteristic of products that are sometimes in specific case required by the code, and they are usually prescribed as per ASTM E136 or CAN-ULC S114. So there's basically two typical standards used in North America to determine the combustibility or non-combustibility of materials, of building materials, I should say. The first one, ASTM E136, is applicable in the US. The second one, CAN-ULC S114, is applicable in Canada. And these two tests will basically evaluate if a product can aid combustion or if it add appreciable heat to an ambient fire. And so materials that will meet the criteria defined by the standards will be considered non-combustible. So in order for material to be non-combustible, it must meet very, very specific and stringent criteria defined in standards and referenced by the code. Again, it's not as simple as saying, for instance, in the case of ROCKWOOL insulation, it's made of rock, it doesn't burn. There's a lot more to it. And so the two standards in between US and Canada, they are very similar in, at least in intent, and they have many similarities, but they are very different in the way they determine the actual non-combustibility. And so the point is that they are not interchangeable. And so whether you're in Canada or in the US, when you look at a specific product to use on your project, you must be sure that you are referencing the correct standards to meet the criteria that you're required to meet. And so they both of them use a furnace. You can see on the left side is the Canadian furnace. On the right side is the US furnace. And you can already see that while they look fairly similar, they are not exactly similar. But both furnaces or in both test method will basically require for the product to be exposed to a temperature of 750 degrees Celsius or about 1400 degrees Fahrenheit. In the US for 30 minutes, when in Canada, it's only for 15 minutes. And basically, the idea will be to look if the product is seeing a weight loss, which obviously will be indicated of combustion. If there is a temperature rise in the furnace, which will indicate that the product is contributing to, is basically fueling the fire. And if there is flaming. This is based on the results for these three criteria, not just one of them, but three at the same time, a product will qualify as combustible or non-combustible. Now, the non-combustibility of material is not the only parameter that is interesting. There is a lot more to the performance of a product when it comes to fire. And throughout history, the flammability characteristics of interfinished materials have played a major role in building fires. And in fact, and I'm sure it probably doesn't come as a surprise to most of us here, the high number of fatalities is typically related to smoke, heavy smoke, and flame. And so in the code, as the years have passed, the burning characteristic of products have become more and more stringent, and especially as they relate to flame spread and smoke generation. It's all over the code, as you can imagine, and I'm sure you've already seen. Whether, again, you look in the US or you look in Canada, you'll see references to flame spread and smoke developed. And so on the top image, so here there's some screenshot from the National Building Code of Canada, from the International Building Code, but here there's one on the top, which I like, which is from the International Mechanical Code, where, for instance, you can see that there is requirements about materials being used in plenums, and the requirement will set maximums for the product performance in terms of flame spread and in terms of smoke developed. Now, there's, again, two standards, one for the US, one for Canada. In the US, it's called ASTM E84. In Canada, it's called ASTM CANULC E102. And they basically both utilize the same apparatus, which we'll see in a photo in a minute, where you will position the sample in a sealing position. It will make more sense when I show what the testing apparatus actually looks like. But both these tests, they basically evaluate the flame spread and the smoke developed as a product is exposed to a fire. And so what this test does is that it will basically measure the speed at which the flame progresses across, from the sample, and it will also measure the amount of smoke that is developed as the sample is exposed to fire. As I'm sure you already guessed, there's two standards, one in the US, one in Canada. It will just be too easy if we could use, for people like me who cover both countries, it will just be too easy and not fun enough if we could have the same standards and exactly the same results. But while the two tests are very similar and have the same intent, they are not interchangeable and they are not equal. Some of the main differences, it can get a little technical here, but I won't go in depth of it. But it will have to do with the air turbulence that is used within the tunnel. But probably much more easy to understand, it has to do with a flame spread calculation. So what it means is, a given product tested by the two standard will not necessarily show the same flame spread number. It also has to do with the number of replicate tests. How many samples do you need to test? And finally, with terminology. And so while we use typically flame spread index and flame spread and smoke developed index when we talk about the performance of product in this specific case, in Canada, they actually often, well, the standard, the most up-to-date standard actually talks about flame spread value and smoke developed value. So it might seem to not be a big deal, but there is a reason why it's different. And one of the reasons, again, is that because the tests are not interchangeable, using different terminology helps realizing that the numbers are not exactly the same, and it should not come as a surprise that they are not the same between the two standards. This is what the tunnel looks like. So this is called a Steiner tunnel. And both standards use the same tunnel. What difference between this, they use the exact same apparatus, it's just how you use the apparatus that is different. And this photo show an ASTM E84 configuration. If you were to look at the Canadian equivalent, it will actually look a little bit different. But anyway, let's see if I can get a pointer here. So hopefully you can see my laser pointer here. So imagine here that you have a furnace with a fire, which I will show in a minute, and you have a fan that basically throws, basically push the fire toward the tunnel. You would position your sample that you're testing in the ceiling position, and that's why you have a window here, so you can actually visualize the sample, you can visualize the furnace, etc. And basically what you're going to look at is you're going to use this window to look and visually look the progression of flames throughout the test. So you'll start at T0, and if you remember, you'll go to up to 30 minutes. You'll do this for a certain duration and see how the flame progresses. And you see there's a little cursor here, and basically imagine the operator during the duration of the test as the flame progresses. The operator will move this little cursor to take the measurement of the progression of the flame. At the end of the tunnel, there's the exhaust hand, and just before it, imagine photo sensors basically that will measure the opacity of the smoke. And by doing this, you can measure how much smoke is developed. So if there is no smoke, the sensor will see, basically 100% of the light. If there is smoke, there will be some opacity, and only so much light will be able to go through that smoke. And that's how you can measure the amount of smoke generated. You can see here there is a full crane and a lid, and so basically when the operator prepares a test, they will remove the lid of that apparatus to prepare everything and then reinstall the lid. This is what the furnace look like. So I'm saying a furnace, maybe I'm not using the right word, I should call it a burner. This is what the burner look like. And so obviously all of this is standardized, the amount of flame, how strong, etc., how much energy is there. All of this is very specifically standardized, and an operator from one of the lab that run this test would probably be able to speak much more precisely than me about how it's actually done. But you can visualize here the burner and imagine the sample installed in the ceiling position a little bit in front of it. This is the operator here moving this cursor. So again, as the test is progressing and potentially the flame is developing, the operator would move this cursor. So full disclosure, ROCKWOOL installation usually has a flame index and smoke develop index of 0. So this test is not very fun to watch when you're testing stone wool installation, because essentially not much happens. But it's basically the idea is the operator will move that cursor to measure the progression of the flame. So how do you read the results for this kind of test? Basically, the lower the numbers, the better. So typical things you will see for ROCKWOOL installation, for instance, will be 0, 0, meaning the flame spread index is 0, the smoke develop index is 0. This is essentially the best result you can get for a product that does not contribute to the flame spread and does not develop smoke. But these numbers will grow as obviously there is smoke developed of flame spread. In the US, there's one thing that you can see that you wouldn't see in Canada, which is classes. So the building code in the US actually define classes to help understanding and comparing products. And so you may be seeing class A, class B, class C, and this will be based on the range of flame spread index or smoke develop index that a product has obtained. And so all of these are informations that you will find on the technical data sheet of a product. So in the case of installation, here's a ROCKWOOL product. This is a screenshot from the data sheet of the product. And what you will see is that on the data sheet, on the reaction to fire, you'll have the flame spread index and the smoke develop index as indicated. And you'll see that the different standards, because many manufacturers obviously sell in both countries. And we'll just have one data sheet because it's more convenient and because a lot of other standards are going to be the same. But in this case, you want to make sure you're looking at the information that is appropriate to where your project is located. And so you'll see this flame spread and smoke develop index as per CME 84 or CANULC S102. And then you'll have the same information provided for non-combustibility as per the Canadian standard and the American standards. And if you pay attention to the technical data sheet, you'll see that sometimes these results will vary because, again, the standards are not absolute-wise, somewhat similar, and using similar testing method, they are not interchangeable, and therefore they may produce slightly different results. Now, I just want to do a quick little side note about wide-learn urban interface design. And this could be a full topic on its own. So obviously here we don't have time to go in depth. But the idea is, and I'm sure, especially I saw in the chat, there were a lot of people on the West Coast, and especially thinking about last summer, there were certainly a lot of wildfires there. But even on the East Coast, and us in Canada or in the northeast of the US, I know everybody was pretty much affected by the wildfires in Canada. So in fact, it probably is relevant to pretty much everybody. But obviously wildfires are, they will happen. But while they are inevitable, the losses to life and property from this fire can be minimized by using building construction methods that reduce the likelihood of building ignition in conjunction with maintaining defensible space to reduce the severity of potential wildfire exposure. So there is an international WE code, and that code is typically referenced then in the local codes, whether it's at the state level, at the provincial level, and etc. And what this declination of the WE code do is that they get more specifics to what would be typical in a given province or state. So there may be things that are being tweaked if you compare the WE code from a certain area to another area, but they are based on the international WE code. And essentially what this code does when it comes to the topic of today, insulation, etc., they will prescribe the use of non-combustible materials on the exterior side, obviously, because in this case, we're talking about fires that are originated outside of the building, but they will also prescribe construction methods to prevent flame and amber intrusion into vents. And this, if you do residential design, you'll be very familiar with the specificities, the things you'll have to think, for instance, with your roof assemblies, where things can get a little more complicated in WE zones. One other side note has to do with the California Department of Forestry and Fire Protection database. And so, so often referred to as CAL FIRE. And so basically, CAL FIRE created a listing program that originally was created to mandate that all fire alarm systems and fire alarm devices be approved and listed in California in order to be sold. And this program was popular and proved to be very useful. And so it was later extended to include other materials. And so insulation products, for instance, can now be included in this database. Now, insulation products are not required to be listed in order to be sold in California, for instance. But the reason why it's relevant to talk about this database is that obviously in California, they've been very proactive about wildfires because of obviously the severity of the wildfires that they have had over time. And so it is essentially a database that will give you a list of materials that are approved for use there, and that you can be sure that if product is listed there, it will, it basically can be used to meet the requirements that you may have in WE zones. And so the intent of this listing is to provide basically to specify a reliable and available information about these materials. And I will do a little bit of a promotion here, but ROCKWOOL Insulation has several of our products on this database. And as of today, it's the only insulation type that you will actually find on this database. So again, one of the reasons is that obviously there are other materials out there that are non-combustible. But the reason why not everybody is in there is because, again, it's not required for insulation material, but it's something nice to have. So this is in a very short time what we can say about the product. Now, the performance of a product is great, if it has a nice reaction, if it's non-combustible and so on, but a product alone will not do good because we obviously use products into assemblies. And so now the next step is to talk about building assembly fire resistance ratings. So the fire resistance rating is defined in part as the time in minutes or hours that a material or assembly of material will withstand the passage of flame and the transmission of heat when exposed to fire under a specified condition that you'll find in the testing methods that we will be talking about in a minute. And the reason why it matters is that fire-rated assemblies are key to giving occupants and firefighters time. So it has to do purely, obviously, with spread of fire and fire safety. The one point I want to make very clear here, and I will come back on this in a little bit, showing photos, is that let's say an assembly that has a 1 hour fire rating is by no means an assembly that will remain intact for 1 hour. It only means that it is an assembly that will be able to resist the passage of flame and will only transmit so much heat and remain, and basically stand during that hourly rating that it has. But it doesn't mean it will be intact. It's only meant to protect, to give time for people to escape, firefighter to act, and for the building basically not to collapse on their heads. And so hourly ratings are all over the codes, which again, I'm sure doesn't come as a surprise for most of us here. Just here are some example, but basically the hourly rating will vary on various things, such as what building element are we talking about? What kind of building? What is the structure of the building? What is it made of? What is the occupancy of the building? So this, I think, is really well known by all of us here, but there's many factors that will affect the hourly rating. So obviously it's, as you're working on your project, you will know what are the requirements that you need to meet. So in US and Canada, there's two standards again, that's gonna be the theme of the day, two standards to assess the hourly rating of an assembly. In the US, we use ASTM E119. In Canada, CAN-ULC S101. And basically, these two standards will assess the performance of wall, columns, floors, and other elements under very defined fire exposure conditions, with the idea of making sure that constructions are safe and that they are not a menace neither to the public nor to the neighboring structure. Obviously, it's not just about giving time for people to evacuate, it's also to give time for firefighters, for instance, to act without having a risk that the fire spread to the neighboring buildings. And so basically the two test methods intend to evaluate the direction for which the type of building elements contains a fire and retain their structural integrity for a certain amount of time. If you look on the photo on the right, it's a photo from a ROCKWOOL test under ASTM 119. So if we were thinking about the Canadian standard, it will look very similar, but this one happens to be tested as per ASTM 119. I will show more photos in a minute, but I would like you to get a quick idea of what that test is about. So what you see here is actually a test being run. You can read here, it's an assembly number 2, and we're testing an inter-exposure. So you can imagine, you'll see a better photo in a minute. You have a furnace, you built a wall, and this is the wall here, this square. This wall is built within a cartridge that is pushed against the furnace. And, in this case, it's an exterior wall. So obviously the interior face of the wall and the exterior face of the wall are not the same. We're testing in this very specific case a stucco wall. So you're seeing stucco applied over exterior insulation, applied over a wood frame wall with batt insulation and interior gypsum as a finish. The side that is being exposed here, again, it says here on the board, it's interior exposure. So the interior face, so the interior gypsum face is exposed to the fire. And the idea for that test is to try to reach a 1 hour fire rating. So as a manufacturer, you'll design a wall with a certain duration in your head. It's not, you don't just run a test and see how far it can go. Where you have to predict what you think the performance will be. So you'll say 1 hour or 2 hours or maybe 45 minutes, and you'll do the test and hope to pass the test. But you basically predict the time and then run the assembly for that specific time. You don't just stop it when you see you're failing. I will also point out to here, it talks about loads in pounds. I will come back on this in a minute. So the two standards, ASTM 119 in the US, CAN-ULC S101 in Canada, again, essentially very similar, essentially the same, but not exactly the same, not interchangeable. But they use both the same time temperature curve and the same performance criteria. What does that mean? The time temperature curve is basically when you have your wall apply against the furnace, you'll start the burners, so you'll start the fire, and you don't just go all in. The fire will build up. The temperature within the furnace will increase because it's an enclosed space. And so basically the temperature will increase over time. That's what that temperature increase is very well standardized and is very precisely controlled during the test. As a matter of fact, here I put it as a screenshot where you see the time on the x-axis and the temperatures on the y-axis, and you see that the temperature will gradually increase over the period of over the time of the test. You know, if you're testing a symmetrical wall, for instance, a partition wall, which let's say is steel studs, batt insulation, and gypsum half-inch gypsum on each side, you will test this wall once, and because the wall is symmetrical, you know, if you meet a 1 hour fire rating, you end up with a 1 hour fire rating. If you're testing an exterior wall, like I was showing before with my stucco wall, because the wall is unsymmetrical, the sides are not the same. In order to get a 1 hour fire rating, you basically need to run 2 tests with 2 samples of this wall. And each time you will expose a different face of the wall to the fire. And only by passing this certain duration for each side, only then, if you pass both sides, you can end up with a 1 hour fire rating. If you can only pass one side or only test for one side, you will end up with something, for instance, such as a 1 hour fire rating interior. So if you look at a UL listing, sometimes you will see it will indicate the fire side, because this wall is not just a 1 hour fire rating, it's a fire rating for when the fire is on a certain side. It's possible to have a wall that can resist a fire from one side for 1 hour, but not from the other side, where in the other side, after 30 minutes, maybe it will fail. Because, you know, obviously the exterior side with exterior insulation protects the structure if the fire is on the exterior side. Now, if the fire is on the inside, the only thing between the fire and the structure, your wood studs, for instance, is a gypsum board. So the performance of the wall is not the same on both sides. So here, this is a photo from a lab that I took. And you can see on the left side, that's what the furnace actually looks like. And so, you know, as I was saying earlier, you have this furnace and you will build a wall, which we'll see in a minute, and you will push it against the furnace. Here you have the burners where the fire actually comes from. And all this like sticks here are basically temperature sensors. There is a proper name for it. I don't remember what it's actually called, but basically this is how you control the temperature in different locations of the furnace. The fire, the temperatures, all of this is very precisely controlled. So you see the furnace here, and you see this frame here, this big metal frame here. This is, and it's hard to see on the photo, but it's actually positioned on wheels. You will understand in a little bit. Actually, you can see the frame here with the wheels. Never mind. So you can actually see this fairly well. And you'll understand why this is on wheels. But basically, this is the wall we're testing here. And it's installed within this cartridge here. And so now this is the same wall, but we're actually testing the other side. So you see now it's no longer the stucco side of that other wall I was showing earlier. It's been reversed. So we're testing the exterior side. So the stucco side is exposed to the fire in this specific example. And this is the interior finish. It's not painted, but it's because you don't need, obviously, it's irrelevant to put the paint here. It wouldn't really, because it's on the other side. But it's basically the interior side. These guys here are your temperature sensors. This basically are the areas where you control the temperature. And here in the white circle, you can see here, there's like pistons. And so the idea is that when you run this test, you may want to run it for what we call load-bearing walls. Because obviously if a fire is exposed, an assembly is exposed to fire and is meant to be load-bearing, as it's you know, going as it's exposed to fire, the fact that it's bearing a load will put even more constraints, even more stress on the wall. Imagine your wood studs are exposed to the fire and starting to consume. Obviously, if there is a load applied on this wall, it's going to push on it and eventually may actually break the wall faster than if the wall was not load bearing. So this test account for this, and this is how you do it. You apply. So it may be surprising it's done from under. It's because it's simpler to do it from under, but obviously the load you're applying on this wall, whether it's from above or below, makes no difference. And this load is very precisely, the amount of load you put is not up to the person running the test. It's obviously very standardized, calculated as per structural code, etc. And so you see here, this is back to our previous wall here. So again, we kind of already saw this wall. This is the stucco side again. On the right photo is the interior side. And here on this photo, the test is running. You can actually see, it's a bit hard to see, but there's actually some smoke here coming out because the wall is obviously going through the test. After a certain duration, so in our case here, I was showing a wall that was going to, for a 1 hour fire rating, meaning the wall is exposed for 1 hour to the fire. After that 1 hour, let's assume the wall seemed to have performed well. Obviously, if the wall was to completely fail after 30 minutes, you will stop the test and just consider that a fail. But here, let's assume our wall worked well. It seemed to perform well during 1 hour. That's not it. You don't get your 1 hour fire rating then because there is an additional test that needs to happen. So you can see here the operator, you understand now why this wall is built within a cartridge on wheels. The operators has removed the piston, the load is no longer relevant. You remove all this. The operator is taking the wall away from the furnace. And you can see here there is a fire hose. You'll understand in a minute why. So this is our wall, and it's probably very hard to tell, but this was the stucco side. And I'm not sure how well you can tell, but basically the stucco is completely gone after this 1 hour fire test. The exterior wall it's obviously been into an extreme fire condition. The stucco is completely gone in this specific test, but it doesn't matter. We're not trying to keep the wall intact, right? We're trying to make sure the flame doesn't go through the wall, and it's very clear on this picture. The interior side looks intact, right? And that's what you're trying to do: control temperature, control passage of flame, etc. But the additional step you need to pass is what's called a fire hose test, and basically the operator will apply with a hose a certain amount of water under a certain pressure for a certain duration, and will go over the wall. And the wall must be able to withstand the pressure from this hose. You don't want to see a hole, or you don't want to, obviously, the wall to collapse under this hose test. The intent is I think, pretty straightforward. The intent is basically to show that this wall, which has a, let's say, 1 hour fire rating, is able to withstand what the fire marshals will have to do to extinguish the fire. So even then, you don't want the wall to collapse. But you can, this is very, very extreme. It's very cool to see. This wall was all non-combustible materials. Think about it: stucco, stone wool insulation in the exterior side of the studs, and within the studs, I say all non-combustible material, not true, but non-combustible insulation and finish, interior gypsum board, and then only wood stud and wood sheathing. But you see how much damage has happened. It's a bit hard on the photo, but it's very impressive to see. And so anyway, you pass this test, you end up with a listing for the duration of the test that you passed. And where do you find this? You basically find this on the database. These are public informations. The listing of this passing assemblies is obviously they are public information, and you'll find this on the databases of the different labs that are accredited to run this test. So for instance, you'll have UL, Intertech, QAI. So one question I often get from people is, oh, I need a UL test for a 1 hour rating. And I'll give them an assembly that has a 1 hour rating, but it's not from UL, it's from Intertech. And sometimes there is some confusion about this. UL is one lab that is accredited to do this test, but so are other labs. And therefore, what the code requires you to have is let's say the code requires for an assembly to have a 1 hour fire rating. What you're required to provide is a listing for a 1 hour fire rate assemblies that was tested for an assembly that was tested from an accredited lab. But UL does not hold more values than Intertech or QAI or other lab. All these labs are accredited to do this test, so their listings have the exact same value. And obviously, each lab will on their database have assemblies that they have tested. So if you limit yourself to UL, you're basically ignoring a bunch of other possibilities that you could have. So very important to have that in mind. This is an example of a listing. So in this case, we're looking at wood stud wall, and I just want to run you through some few things here. It's actually very easy to read most of these listings. But what you see here is, so this wall was tested by QAI. So it has a QAI design. It was a test done by ROCKWOOL. So ROCKWOOL is the owner of this listing. It's for an exterior wall. It was tested. It complies to both CAN ULC S101 and ASTM E119. So it's valid in both countries. This specific wall achieved a 2-hour fire rating, and it's load bearing. And the 2-hour indicates there is no precision about if it's interior or exterior, because this 2-hour fire rating is from both sides. This will pass the 2-hour rating for both sides. And then what you see here is basically the wall described component by component, from interior gypsum, the bat, the stud, the sheathing, the exterior insulation, the flooring strip, the cladding. And when you use this listing, as most of you probably already know, you must, in order for this listing to be applicable, you must follow line by line, word by word, what this listing describes. If you change one component, the listing is no longer applicable. Even if you change one non-combustible component for another that is not listed in the listing, you must build the listing as per the listing word for word. Now, this listing are made to be as generic as possible. May be hard to read, but if you look, for instance, at the stud here, it will say minimum size 2x4. Minimum size. What it means is you can use 2x6. Maximum spacing, 24 inches on center. So obviously you can do your stud at 16 inches on center. Exterior insulation using comfort board with a minimum thickness of 4 inches. So you can obviously use 5 or 6. Exterior cladding, terracotta plank, fiber cement, stucco, wood base. So again, these listings are written in a way that they provide multiple options as often as possible. But you must use whichever assembly you're building. If you want to follow a specific listing, your option must be obviously word for word what's in the listing. Last piece, I already kind of talked about it a little bit. Here is the piece that talks about the load-bearing component. And so in this case, the wall is approved as a load-bearing wall with no restrictions, meaning that as per the structural codes that applies, it can carry 100% of that load. And so this, you want to be very cautious, because some listings probably during the test were not able to carry the load. And so they were, basically the people running the test decided to remove the load to try to get a listing for like a restricted load-bearing wall or non-load-bearing wall, meaning this listing is still valid, but the wall will have restrictions. So in the residential home, usually your exterior walls are going to be load-bearing. But on commercial construction, for instance, it's obviously possible that some assemblies and the exterior envelope, for instance, that don't need to be load-bearing. So these are things you want to be very cautious with. Okay, and moving on to finish, I would like to speak about facade performance, because obviously this hourly rating, they apply to exterior wall, but also partition walls and lots of different configurations. Now I would like to specifically talk about exterior walls, and especially exterior walls that are of a certain height. You may have heard about this fire. You may remember it in 2008, the Monte Carlo fire in Las Vegas. What happened here is basically the fire started in one unit, spread, broke through the window and spread along the facade, and eventually the whole top of the building caught on fire. Very extreme thing. Grenfell, more recent, 2017. So it was not in North America, it was in the UK. I think most of us are probably familiar with this. It was an absolutely dramatic event, extremely sad. The fire broke into a unit on the lower floor. And again, broke through the window. Obviously, glass does not resist very long to fire, like typical glass from typical windows that we use. And the fire spread throughout the facade because of the insulation and the ventilation, etc. There is a lot of information out there. But in no time, the whole facade caught on fire. And unfortunately, there were some fatalities. So very, very extreme events. So there's reasons that I'm obviously not going to go over here, and plus I'm not an expert in this case. But just like in Europe and even in the UK, as a matter of fact, even though when you see this, it doesn't look obvious, but obviously we have a lot of regulations to prevent this from happening. And the need to regulate come from, various things, such as, the fact that if you go a while back, North America, it's been a good amount of time that we really regulate. But if you go a while back, there was no like full scale test, and there was maybe a lack of code requirement for fire performance of exterior walls, lack of enforcement of the code, etc. But so nowadays we have multi-story fire testing required by the code, both in Canada and the US. And it will apply for specific type of construction when the building is a certain height. Usually there is a minimum height above which it applies. Two different standards again in the US and FPA 25, in Canada, CAN-ULC S134. And so essentially these two tests are again very similar, especially in intent, even in the method of testing, but they are not exactly the same. One more time, they are not interchangeable. So if you're in Canada, you want to make sure if you're required to have a passing test for a facade, you want to make sure you use S134 in the US and FPA 25. And it's interesting to note, CAN-ULC S134 is typically more stringent. And so it is very possible, just like the hourly rating I was showing earlier, where it was actually covering the two standards, it is possible to find some of this listing that will basically be applicable with both standards, depending on what was tested and how. Now, one thing to note here, like STME 119, for instance, it's an hourly rating. So you test the product, you end up with a 1 hour, 2 hour, 1.5 hour fire rating. In this case here, we're not talking about any sort of rating. We're talking about purely a pass or fail. And so if the code requires you to have an FPA 25 compliant assembly or a CAN-ULC S134 compliant assembly, you must find an assembly listing and build the assembly that has passed this test. There is no performance within that listing. It's a pass or fail. The test procedures are quite similar, but basically in this test, you will look at the flame height and the temperature or intensity of the heat flow. What you want is to make sure that the flame does not exceed a certain height during the duration of the test. And the determination of passing result will be based on flame propagation on the front wall surface and the heat or temperature at various locations. You want to make sure the temperature does not increase a certain amount on the floor above. And so the additional piece that is interesting is this test, like when you have a building a certain height, and the code will require you to have a facade that comply with this test, that has passed this test, but it only applies if you are using materials that are combustible. So for instance, if you're using non-combustible cavity rock, which is a ROCKWOOL insulation product, the insulation on its own, because it's non-combustible, will not trigger the requirement to have a passing test for your assembly. If you use non-combustible cladding, non-combustible cladding attachment system, non-combustible insulation, you don't need to have a passing test. You only need to have that if you have some combustible materials. And so usually the people who will do this test are like the people who make combustible claddings or combustible cladding attachment systems, or combustible insulation, because they basically want to provide solutions with their products that will comply. Now, if you have an assembly with a combustible cladding and a non-combustible insulation, well, you do need to have a complying test, right? So, but if you design only with non-combustible material, you don't need to comply. You remember this photo, we focused on the left side. Now we're going to focus on the right side of the slide. This is what the assembly, the furnace looks like. So basically now you have an apparatus with an intermediate flow, two rooms, one above the other, and you have a burner inside the room. You will put your wall against the apparatus. In this wall, you have a window, because the idea of that test is to see what will happen if you have a fire that breaks into a room, breaks through the window, and spread along the facade. And is the next floor basically, is a fire basically going to spread to the floor above? So in this test, you have a floor above and you have a window. So you'll see this on the next photo. And here you have it. So you have the furnace. This is the intermediate flow here. I know it's a bit hard to understand, and I absolutely invite everybody to try to find a way to witness one of these tests. We at ROCKWOOL, for instance, we've not done many times, but we love sometimes to have it. Obviously, it's a lab, it's dangerous, there is fire. Love to have, whenever we do this test, to have to invite people to witness this. We don't do it often. We really should. But I think as a designer, there's an absolutely great value to witness this, just to understand what it actually means and to feel the performance of materials. But anyway, you have your window here. You can imagine you had the room below, the room above. The fire starts it started with a burner inside the room. And is spreading around by the window and gets to the facade. You will notice there is a secondary burner outside, and that burner will start after a certain amount in the test. The purpose of that burner is to make sure the facade sees fires. because you don't want to have, let's imagine you have very good interfinishes and somehow the fire that's sitting inside doesn't spread to the exterior facade. You know, the test will only be so useful. You really want to test what happens if the fire gets to the facade. And so in fact, in this test, you have a burner inside, but after sometimes you even have a burner outside to make sure you have fire against the exterior facade. You also notice in this test, there is no exterior cladding. And that's because in this specific case, we really wanted to test the performance of the insulation in this configuration. And in this test, basically, you imagine that if you were to add a non-combustible cladding, it will not change anything to the result. If anything, it will make the result of the performance of the assembly even better. So this test is tested without this assembly is tested without any cladding. But in the listing, you will end up with this assembly plus, you know, a bunch of non-combustible cladding installed over it. But so that's basically what the assembly looks like. And finally, as I'm sure you could imagine, you end up with a listing. So this is an example from Intertech now. And you can see here that you have, it's an NFPA 25 listing. And in this specific listing, it includes various assembly. So you can see here, this is a front page that talks about the different materials that are referenced in this listing. But then here, you will see the first assembly within this listing. It says NFPA 25. So again, here, it just says rating meets condition of acceptance because there is no, either you pass or you fail. So there is no additional information. And you have the products that are referenced into this test. And here, line by line, you're gonna have every single components detailed. And in order to have a compliant assembly, you must build an assembly that is exactly similar again than what the one that is described. What you can also maybe see here, for instance, with the steel framing gauge, is that the listings, just like the hourly ratings, they are written in a way that they will allow for as many options as possible, right? So you're usually not gonna have just the one cladding, you're gonna have multiple cladding, for instance, or not just the one insulation, multiple products, or not just the one cladding attachment system, you're gonna have multiples, right? So that's what you wanna use. And last thing I wanna say now, before I let Manaz conclude this presentation, is that way too often my department, we get contacted for on a project because you know, let's say an assembly has been designed and we're being asked, do you have a 1 hour fire rating, or do you have an NFPA 25 listing for this assembly? And guess what? The odds of saying yes to this is about I don't know, but probably 1 in a billion, because there's just too many variables. So when you're working on a project and you need to have either compliant assemblies with an FPA 25 or CAN ULCS 134, or you need an hourly rating, what I would always recommend is to kind of roughly define what kind of assembly you want to use, and then first look for a listing, as opposed to design the assembly and then find a listing that matches your assembly, because the odds of finding this are just too low. Even though there is so many, there's hundreds, probably thousands of assemblies tested out there. So first, once you roughly know, I'm using wood studs, I'm using steel studs, I want siding, I want, you know, this kind of cladding, I want ACM, whatever that is, define roughly what you're looking for, then find the assembly listing, and then design your assembly. And now I will pass it to Manaz.
Thank you. Thank you, Antoine. Thank you for enlightening us on fire properties of products, of fire resistance ratings for building assemblies, the WUI codes. I really appreciate the info. That's why we're here. So I'm going to resume the presentation to talk about a few products that you might come across or that you might be using when you're doing passive house projects. So for example, there's Cavity Rock, which is our exterior insulation material, which was used in this passive house project by Perkins and Will. It's the University of Victoria Student Housing and Dining, 621 units. And I think this has actually been showcased in the Passive House Accelerator at some point. Then we have Curtain Rock, that's, excuse me, Curtain Rock 40 or Curtain Rock 80, depending on the fire requirements. In this project, the Winthrop Center in Boston, Massachusetts, the world's largest passive house office project by Handel Architects and Stephen Winter Associates. So you've probably heard about this project. And additionally to that, you have ROCKWOOL Safe being used in there for the perimeter fire safing. This project is also something that you've probably seen at the Passive House Accelerator. So ROCKWOOL insulation can be used as a component of an eave system. In this case, it's a component of the Durock puck system. This is the Ken Sobel Tower in Hamilton, Ontario, and it's, I think, the world's largest Passive House retrofit certified, so NRFit project by ERA Architects. This is another example of using a ROCKWOOL product in an eave system. So this time we're using Front Rock as a component of the Drive It eave system on a project that you probably know, which is Engine 16 in New York City. It's a Passive House retrofit by Baxt Architects. And this one here is a project where we're using Comfort Bat. So Comfort Bat is our thermal insulation that you will be using on any sort of project on the inside of exterior walls. And here it's used in combination with Comfort Board, so our rigid board insulation on the Bella Bella project in Bella Bella, British Columbia. So this was a modular passive house project by Mobius Architecture. So if you want to discuss projects or details, Robert and I, we are available for you or the colleagues of ours in the regions. We also do lunch and learns, product presentations. Please contact us. Supporting us is the Technical Services Department, which you can contact for assistance as well. We actually have a bilingual team, so they're helping us out. They're there for you. And then we're also very proud of the services offered by the building science team. The services offered are shown here. This team can help with general building science support. They do thermal analysis, calculating effective R values using 2 or 3 dimensional analysis methods. They do hygrothermal analysis, and they're also able to do acoustic modeling. So we're really trying to support you with our different teams, with our presence, with our knowledge, for you to achieve better buildings. And this is really the end of the presentation. I hope you've enjoyed it as much as I have. Do you have any questions?
Wow, yes, there are questions for sure. And Manaz, Antoine, and Rob, just thank you so much. What a masterclass in combustibility and non-combustibility. And I think that that Hans Eich spoke for the audience when he said, I just wanted to take a moment to show my appreciation for this presentation. Very, very interesting, and a lot of details I never knew. I think all of us got this kind of deep dive into this world of fire testing that is that we don't really get to see typically. So thank you very much. We do have some questions, and we also have some space for more. So feel free to type your question into the chat. The first question comes from Mackenzie Stickney. If Mackenzie, I know that this was discussed in chat, but I think it'd be useful to hear the conversation about it. It looks like Mackenzie had to take off probably at the top of the hour, but Mackenzie asks, how does the rock... Oh, you're here. Oh, great. Good.
Yeah.
Good.
Hi.
Thanks.
Yeah, I asked this right as the presentation got started. And I have a follow-up question because it was more about fire rating than installation. But in the office, we often talk about the compression that happens using different exterior installations. And I guess I have 2 questions about how to minimize compression. And you talked about it a little bit. I had to sneak out for about 5 minutes, but if there was a rule of thumb about what rain screens ROCKWOOL would recommend to maintain the fire rating as much as possible. I know that there's a million different assemblies and people do things different ways, but if there was a rule of thumb about furring strips or attachment styles that maintain the fire rating.
Okay, so the first one is about compression. I assume you are thinking about compression of exterior insulation when you're installing siding and furring strip over it. Is that correct? Yeah.
Yeah, that's it.
Okay, so that's it's the first very easy way to respond to this is experience will help with this, experience of the contractor. However, solutions that are being used out there is, for instance, to use like little wood shims behind the flooring strips or solid pieces of the thickness of the insulation that can be positioned in certain key location, which will allow that when the contractor is fastening the flooring through the insulation to the stud, that the flooring, that it will not overdrive the fastener and compress the insulation. So experience, and then using shims or like little blocks behind the flooring strips to ensure in a few locations that it will maintain the thickness of the insulation. The second piece about the rule of thumb for I guess the type of flooring strips, the siding, the insulation thickness, I wish I could answer this easily. There's not a lot of rule of thumb, and it really depends. First of all, what is the hourly rating you're looking for? So let's assume it's a 1 hour rating for an exterior wall. Obviously, and I'm a bit biased here, but obviously using non-combustible insulation, I will let you figure out which kind will help. But usually to get a 1 hour fire rating, you're probably going to be looking at a few inches, like 1 or 2 inches, if you're using a combustible cladding and combustible flooring strips. Now, if you're using non-combustible cladding and non-combustible flooring strips, you may be able to reduce that insulation thickness. But I don't think there is really a rule of thumb. And that's exactly why, to me, the way to go when you need to have an hourly rated exterior wall, the best way is to determine roughly what you want to have as a wall and finishes, and then directly go look at what listing there are out there, because there is no rule of thumb, and therefore it's very unlikely that applying basic rules and designing a wall will result in finding an existing listing afterward. There's just too many variables.
Thank you.
Thanks, Mackenzie. Thanks, Antoine. Okay, next up we have James Hui, and Tonya, I also see that you have your hand raised, so we'll come to you after Jesse Elliott. We'll put you on the queue there. So James, are you here to ask your question? I don't think so. So James asks, I'm curious, with the fire rated wall pick exposed to the furnace, is the rated wall assembled in rolls in between studs or a whole ROCKWOOL sheet?
Okay, so is asking for the inter-side testing, whether or not there's batt insulation between the studs. Is that what the question is?
I think so. Is the rated wall assembled in rolls in between studs, right? Or a whole ROCKWOOL sheet? Yeah.
So in the test, when you do this test, you have to build the assembly as it will be built on site. So there is no special tricks about the dimensions of boards and gaps between boards and any of this. So if it's batt insulation between studs, you use the batts that you will get, you will be able to get if as a contractor. So the assembly is built exactly as you will do on site with the materials that any of us can buy in the stores. Now, I'm not sure if the question also has to do with whether or not there is batt insulation to help with the fire. In the specific case I showed, there was batt insulation installed between the framing, but obviously there are solutions out there where there's no batt insulation between the framing. But in order to get, I guess it goes also to Mackenzie's point earlier about the fire rating. Obviously, having non-combustible batt insulation between a wood framing, for instance, is going to help usually with the fire, because it will provide some protection. It will cover the studs with a material that is not going to ignite, which is to some extent going to block the passage of flame. So in the specific case I showed, there was batt insulation installed between 16 wood studs at 16 inches on center. But again, all options exist out there. There's so many configuration and possibilities. I hope this answered the question. I'm not sure I fully understood it, but I hope that answers the question.
Thank you. I think that does. And so let's move on to Jesse Elliott. Jesse, are you here? I think I'll ask Jesse's question. So Jesse asks, we specify mineral wool insulation a lot and see mineral wool VE'd out a lot for fiberglass. Do you have any side-by-side tests or anecdotes for what level of extra fire protection mineral wool is providing inside stud cavities over fiberglass?
So we do, but again, the conversation is much more complicated. There are hourly rated walls with other materials than stone wool insulation, right? Stone wool insulation is not the only answer, obviously, and is not the only material that can work. And so there are assemblies out there that will perform exactly, you're looking at an hourly rating. Let's say it's a 1 hour fire rating, fire rated wall. It is possible that you end the test, but the wall could still do 1 more hour. But we never know because you have to stop the test to finish and do the hose piece. And so once you pass 1 hour, if your goal was to meet 1 hour rating, you don't really just leave it 30 minutes more just to see, thinking, I'm going to get an extra 30 minutes, because these tests obviously are very costly. And so, once you get to the point you want, you still have the hose test to do. So you basically stop the furnace, take the wall. So it's very difficult to fully compare side-by-side wall assemblies. But there's obviously a lot of walls out there which have stone wool batt insulation in the stud cavity that with a certain rating, and you have the equivalent with fiberglass. So the conversation, I'm very cautious, and ultimately when it comes to fire, it's the same as when it comes to thermal, when it comes to acoustic. The product is, there's only so much direct product comparison you can do there. I am absolutely in favor of comparing performance of assemblies and not focusing too much on products. So obviously, stone wool insulation is highly resistant to fire. It has a very high melting point. Fiberglass tends to melt. The melting point temperature of fiberglass is in the range of 400 to 600 degrees Celsius, right? So I don't exactly remember the number, and it's going to vary obviously from one manufacturer to another. But on one hand, you have fiberglass that is going to melt around that temperature range, when stone wool insulation will not melt before at least double of the temperature. So obviously, stone wool insulation alone will provide much more fire resistance and will increase the endurance of the assembly. Now, you will find assemblies out there that can work very well with fiberglass, and obviously with other materials as well. So direct comparison, again, I think you have to be careful with this and what you're actually trying to achieve. And so I definitely don't want to be, the stone wool product, because by nature has a very high performance, in a fire condition. It will not melt, it will not make smoke and flame, etc., and spread flame, etc. But you may have assemblies that work with stone wool insulation and that also works with fiberglass. So probably not the best answer.
No,
I want to be cautious. I don't want to be misleading and make people think that fiberglass will not work. It is okay to be in an hourly rated assemblies as long as the listing allows for fiberglass to be used. As long as you comply with what's in the listing, then you're good.
Yeah, no, I think that's fantastic and very thorough. I also want to share a comment from Eric Reinhardt. This has been a super presentation. Thanks to all of you. Antoine is an expert's expert. I think that the thoroughness of your answer is reflected there. So up next, Tonya, I hope I'm pronouncing that correctly. You had a question.
Did great. You did great. Thank you so much for taking my question. So I'm coming with a question from a slightly different space. I'm not a contractor or an architect. I'm actually someone who lost their home in a wildfire in California in 2020 and built a passive home as a result of that, to reduce the risk of our home burning down again. And so we're safely home for over 1.5 years now and love our new passive home. I'm also working in the disaster recovery space. I'm the executive director of the long-term recovery group of Santa Cruz County. And we are bringing in the Mennonite Disaster Services this year to start building volunteer rebuilds for families that are or underinsured in our county. They're already doing a lot. They're using fire safe siding, fire safe roofing. They're eliminating any combustible railings or decking outside of the homes, but they have not yet sort of entered into the field of insulation. And I think it's a very, very important part. Our home has cellulose insulation, which was conscious decision because it stops fire, and I'm really excited to hear about ROCKWOOL's ability to do this as well. And my question is, is there any interest in collaborating with organizations, 501c3s like our own, that are working specifically to increase fire resiliency in fire rebuilds? So when we're rebuilding homes in areas that have lost a lot of homes to wildfire, if there's any interest in collaboration, potential sponsorships, so that we can help each other get the information out about your products in the communities where many hundreds of homes are being rebuilt, while also making sure that the homes that we're rebuilding in the WUI are as fire resilient as possible.
First of all, I want to say I'm very sorry to hear about the loss of the home, because I mean, I cannot imagine personally what it's like. And, you know, I hope I never have to go through this. But I suppose the exciting piece is that you're rebuilding a passive house, and I wish I could be saying that I'm building a passive house for myself. So I guess with bad things comes good things, and hopefully everything now is much better. Now to your question, yes, obviously we're interested to have discussions about this. It's, you know, fire is the absolute core of what fire safety, fire resiliency, and all these concepts are the absolute core of what we do and what we believe in. And so, you know, I would love to, and I'm sure Manaz and Robert here would also love to be part of this, but we would love to have a conversation offline and, you know, understand you know, what you guys do, and how we could help. So our informations are on the screen, and yes, we would absolutely love to have a conversation about this.
Thank you,
Tonya, I'm
Antoine.
also posting the, sorry, Zach. I'm also posting the email for our architectural rep in California. So if when you email us, please do include her.
Thanks, Rob. Thanks, Tonya. And as soon as I heard your voice, I recognized you. My colleague Alex Wittick had the chance to visit with you and your partner and at your new house and do a video project about it, which is really powerful. So I thank you for doing that, and I included a link in the chat here, so in case folks are curious. And Be Public did such a nice job too. It's a beautiful house. So thank you. All right. So next up we have Kevin Silvera. Kevin, are you still here? Yes, looks like it. I'll give you a moment to unmute. Looks like maybe you're struggling with that. So let me ask on your behalf. So I would like to know, what are the inputs required for acoustic analysis?
Okay, so I guess a very precise assembly description or acoustic target. So the acoustic target could be an STC rating or ITC rating, and the assembly description, obviously in the design phase, you know, may not be super precise. But when we do acoustic modeling or testing, you know, we like to know, is it a wood stud wall? Is it a steel frame wall? Is it an exterior wall, partition wall? So the same things, I would say, as much information as available in order for us to know where to start and what we're trying to achieve.
Fantastic. I think that brings us to the end of our questions. So if I'm wrong and we're missing you, please say so now in chat. But this is, go ahead.
Manas here. I just wanted to add to that, when we're looking at building science services, we typically work through local architectural managers such as Robert and myself, if they're available, to have a loop in with the local person, and then through to the building science team that is part of Antoine's technical department. Excellent. So the best thing is to reach out to Robert or myself, or we can share actually the contact. We should share the contacts of the different architectural resources that we have.
Excellent. Well, thank you. Really fantastic component spotlight. We really appreciate all of the expertise that you've shared. And a big thank you to ROCKWOOL for your support of Passive House Accelerator. Thanks everybody for being here. It was a great audience, great questions, great discussion. And I hope everyone enjoys the rest of your Thursday. Be well.
Thank you.
Thank you, everyone. Have a good day.
Yeah, take care.
Thanks.